Hi guys, I was out sick today and I'm making this video in case I end up being out sick again tomorrow. So this is for the very first part of section 2.5, and I have 2.5 split up into multiple parts. And 2.5 is more on limits and also continuity. For this very first part, we're just going to focus on the properties of limits, and they're pretty straightforward. So kind of like functions, right, or evaluating functions, when we're applying these properties of limits, we're essentially taking the limit of each piece of a function. So for example, this first property here, addition or subtraction, means that if we're taking the limit of like a polynomial function, where you have a string of terms that are connected by addition or subtraction, you can take the limit of, as x approaches some constant of each term, and that will give you what the limit actually is, right? If you think about just, I've told you guys to use direct substitution before, where you substitute c in for x, that's essentially what you're applying here, is this first property, okay? We have the constant multiple property, where if you have a function that's being multiplied by a constant, you can pull that constant out front of the limit and then just take the limit of the function as x approaches c. We have multiplication, so if we have a function that we could think of as being created from multiplying two other functions, then we can take the limit of each factor as x approaches c to get that limit. Division, same kind of thought. Exponentiation, so if you have the limit of a function where you could think of the function as being raised to a power, so even like, for example, if we were taking the limit of x squared as x approaches c, you could think of pulling the x or the square outside and then taking the limit of x as x approaches to c. And then composition is a little bit different, or not as straightforward as the other properties, but it says that if we have a limit of g of x as x approaches c being equal to L, then if we're taking the limit of f composed with the function g as x approaches to c, then this limit will be equal to the limit of, as x approaches L, of the outer function f of x, and we'll do some examples with that. So just to note, in general, the limit can be taken of each piece of an expression, or whatever the function is that you're taking the limit of. You can take the limit of each piece and then put the results of all those limits back together to determine what the actual limit is. Okay, so here's kind of our first example where we're going to be applying our limit properties. So we're not actually given what any of these functions are. We don't know what f of x is, what g of x is, or h of x is. Sorry, phone's going into low power mode. But we don't need to know what they are to evaluate these limits. Okay, so here I would be applying first that first property of addition or subtraction, where we can actually take the limit as x approaches to 3 of 2 times f of x minus the limit as x approaches 3 of 4 times g of x. Okay, and then applying the second property on our list of limits, notice how we have 2 times f of x and 4 times g of x. We can actually pull out the 2 in front of the limit, and you're not going to have to write all of these steps after you become comfortable with knowing what those properties are and how to apply them. Okay, so now I can see that, okay, I have 2 times the limit of f of x as x approaches 3. Well, I know what that's equal to. That's equal to 8. So I'll have 2 times 8 minus 4 times, I know the limit of g of x as x approaches 3 is negative 2. And now I can see that that simplifies to be 16 plus 8, which is 24. Okay. For this next one, we're taking the limit as x approaches 3 of 2 times g of x all squared. So I can actually pull the square out. So we have the limit as x approaches 3, and I'll actually pull that 2 out as well in front of the limit. So the limit's right up next to the g of x. Okay. And now I know what the limit of g of x is as x approaches 3. So I can substitute the negative 2 in. And then we simplify to get 16. Not so bad, right? All right, this last one, C, is a little bit, just looks a little bit scarier, but it's not. Let's try doing it without actually writing all of these extra steps. So by applying our limit properties, okay, we're taking the limit as x approaches 3 of each piece in here. So I'll have the cube root, and then the limit as x approaches 3 of f of x is 8, so I can substitute 8 in. The limit as x approaches 3 of g of x is negative 2. I can substitute negative 2 in for there. Okay. And then the limit as x approaches 3 of h of x is going to be 0. And notice here, this isn't a function, this is just x. So I can use direct substitution and just substitute 3 in for x. Okay, and now it's just simplifying. This will be 0. Cube root of 8 is 2. So this simplifies to be negative, equal to negative 1. Okay. All right, so here's kind of a different type of problem, but the same idea. So now instead of being given the values of the limits of the functions, we have the graphs here, okay? So if we want to find this limit, okay, this is saying we'll have 2 times the limit as x approaches 0 of f of x, okay, that's being squared, and then plus 3 times the limit as x approaches 0 of g of x. Okay, so you'll see that we're really just taking the limit as x approaches whatever the value, this value is, the constant of each function and each variable that's in the expression here. Okay, so looking at the graph, so the limit of our function f, so I go to the graph of f, as x approaches 0, it looks like the y values are approaching 2. And then the limit of g as x approaches 0, it looks like the y values are approaching 0. Okay, so that'll simplify to just be equal to 4. Okay. Running out of room over here. Let's see how I can do this. So notice I just have the variable here, x squared, so I can just substitute 3 in. Okay, the limit as x approaches 3 of g of x, as x approaches 3, it looks like y is approaching 1. Okay, and then the limit, I go back to the graph of f, so the limit as x approaches 3 of f of x, 3's over here, is going to be, it looks like negative 1. Okay, so that'll simplify to be negative 9. Okay, and then, we have composition here, g composed with f. So I'm going to look at the limit as x approaches negative 3 of the inside function first. So the limit as x approaches negative 3 of the inside function f looks like it is negative 1. So this will be equivalent to the limit as x approaches negative 1. Okay, right? That's the limit of the inside function of the outside function. So now I can look over at the graph of g and say, okay, well, as x is approaching negative 1, it looks like g is approaching positive 1, or y values are approaching positive 1. Remember, we don't actually care what's happening at negative 1, we just care what's happening as we get in the neighborhood of negative 1. Okay, now the limit of g being evaluated at x squared as x approaches negative 1. This is actually similar to this example. Now we don't have the graph of x squared, but we know what it looks like. We know it's a smooth continuous function. If I were to substitute negative 1 in for x, that would be equal to 1. So this is equivalent to the limit as x approaches 1 of g of x. Okay, so we look over here, the limit as x approaches 1, it looks like is equal to negative 1. Okay, and, oh, look, we have a one-sided limit. So this is the limit as x approaches negative 1 from the left. We'll have 2 times the limit of f of x as x approaches negative 1 from the left. Looks like it's 1. And then the limit as x approaches negative 1 from the left of g looks like it's going to be positive 1, and that's being squared. So that'll be equal to 2. Did I miss something? As x approaches negative 1 from the left. Yeah. Okay. So the limit as x approaches negative 1 for this last function, we just have 5 minus the square root. I can substitute negative 1 in for x. And the limit as x approaches negative 1, where are we? We're over here in graph f, of the function f of x, oh, that limit doesn't exist. So guess what? We have to just say the limit dne does not exist, because that one part, the limit doesn't exist. Okay, I had a different answer here earlier, but that looks okay. From the left. Yes. All right, and the last thing that I'm going to talk about in this first part of 2.5 is the squeeze theorem, also known as the sandwich theorem, and you'll see why. So what it says is that if we have this compound inequality, which we read from left to right, so if g of x is less than or equal to f of x, and f of x is less than or equal to h of x, okay, for all x, except possibly at x equals to c, and if the limit as x approaches c of g of x is equal to L, and so is the limit as x approaches c of h of x, then the limit of f of x as x approaches c is equal to L. So basically, if this is true, okay, then we can say, and the limit of g of x as x approaches some constant and the limit of h of x as x approaches some constant are equal, okay, then it means that this limit as x approaches c of f of x must also be equal to that same limit. Okay, and here's kind of a picture of what a possible graph could be. So where, and this can be for over some interval, this says for all x, but it's for all x in some interval. So if we have this function h of x, okay, and a function f of x, okay, and then you can see g is right between, oh, I should have that renamed. Let's name this one f of x. And let's name this one g of x. Sorry about that, you guys. Okay, so if this is f of x and this is g of x, this is h of x, we can see f of x is kind of sandwiched between those two functions. Get the sandwich theorem. So as x is approaching a from the left and right, h of x is approaching L, g of x is approaching L, so that must mean that the function f of x is also approaching L. Okay, we're going to deal, so if you have a function that is everywhere contained between two other functions, then at the point where the two outer functions are sandwiched or squeezed together through a single point, then the one in between them must pass through that point as well. You can kind of think about like if you were leaving like a sporting event or a concert and there's thousands of people leaving and then they all end up having to leave through one turnstile. Okay, they get like squeezed through one turnstile. Okay, so let's look at some examples. Well, actually I have one example and then you guys will have some problems, and we're just going to deal with this kind of problem for our class, but you can get more advanced with applying squeeze theorem for evaluating limits, and squeeze theorem kind of shows up throughout calculus. Okay, so if we have negative 3x less than or equal to the function g of x, and g of x less than or equal to the function x squared plus x plus 3, we don't actually need to know what g of x is. We don't need to know what that function is, but we know it's a function that lies between these two functions. Okay, so for all real numbers, these are both polynomials, right? Smooth continuous curves. For all real numbers, the y values of negative 3x will be less than or equal to the y values of g of x, and the y values of x squared plus x plus 3 will be greater than or equal to the y values of g of x. Okay, so the first thing, there's 3 steps that we're going to follow to justify what the limit as x approaches negative 1 of g of x is. So first, we have to state the inequality. Okay, so since this is true, okay, and now let's think about these functions as being kind of the bread of a sandwich, and then g of x is whatever's inside your sandwich. Okay, so these two functions are squeezing this middle function, or they're sandwiching it together. So if we take the limit as the bottom piece of bread as x approaches negative 1. Okay, we could just use direct substitution, and we know negative 3 times negative 1 is equal to 3. Okay, and then we can also take the limit as x approaches negative 1 of the top piece of bread of the sandwich. So x squared plus x plus 3, and again using direct substitution. Okay, we also get that limit is equal to 3. So because this is true, because these two limits are equal, okay, we can say that by the squeeze theorem, or you can say this the sandwich theorem if you like that name better. By the squeeze theorem, the limit as x approaches negative 1 of g of x must be equal to 3 as well. Finito. Not too bad. All right, you guys will have some practice of problems that are similar to the ones we did in these examples to do now.